So I guess your assignment 1 is due today, right? So was it okay? Was it doable? 할만했죠? Only 8 questions should be okay. Should be okay. I started getting the questions on your second assignment, assignment 1.1. But hopefully I can discuss more sometime next week. Start discussing with your friends. That would be nice. And this is your first assignment, so I usually upload the solutions sometime this week, end of this week probably. And you will compare your own answers to the solutions that I upload to Hanyang In. Solutions will be up there only for 2 days. Okay, after 2 days I will take it off, take it out, and don't send me an email to give me a solution. I'm sure your friends will probably have downloaded it, so try to share your solutions between your friends. Okay, there's a reason that I only put up the solution for just short, for a couple of days. I'll explain that later as well. So, make sure you have photocopy of your solutions of assignment 1 today, right? Before you give me a 1 copy. Those of you who've done it in the computer, then okay. But those of you who did it pen and pencil, then do a photocopy and give me 1. Okay. Assignment 2 will be uploaded soon, sometime this week as well. Assignment 2도 이번 주에 나갈 거예요. So you can start right away as well. Okay, so we were discussing what last class? We started discussing something called von Neumann architecture, right? So, but it wasn't that much. It was just basically the computer structures that we already know, like CPUs, memories. But they say ALUs, control units, and then I/O devices. Things that we all know. Another concept they try to, von Neumann architecture try to propose was memory programs in the memory. And we will read data from the memory and start executing the program that we wanted to run. Right? 그지? Why? 왜 그래? Are you still doing your assignment? 아니잖아. 와. 왜 이렇게 집중이 안 되지? 왜 이렇게 어수선하지? I saw a lot of people wearing a high school uniform yesterday. 이게 뭐야? 요즘에 그게 유행이야? 이렇게 신문에 나오고 요새 학교 오니까 여러분 중에서 입은 사람 많대. I thought that's very weird. But 근데 you guys doesn't look like high school kids anymore, even if you wear a uniform. So we start discussing something like memory structure, right? 2 to the ends, and memory I usually draw in a box figure like that. Start from location 0 to 2 to the end. Depends on how many bits that you have, right? We try to draw that in the figure. And there was something called registers. We discussed there are 2 different type of registers that we mentioned. Right? Memory address registers, memory data registers. It's the small place that we try to store a location address of the memory to be read from, right? And it's also consisted of a 2-dimensional array format, 그렇죠? 2-dimensional box. And then there was some slide indicating how do you find a location of that particular place in the memory. What was the one way they suggested? How was the address was constructed? What was the address format that we have looked at last class? 뭐였어? First half of bit was referring to a row. Second half of the bit was referring to a column information. You decode it. Decoder, encoder, we briefly looked at it. Basically, if you give a certain bits, they will give me a large number of bits, so we can find it within the memory location, right? 아니야? Am I speaking completely something new? 왜 그래? I was referring to this figure, right? So you give me first half of the bit to the decoder circuit. This will give me a location, a certain address within this memory, row spaces. And then the second half of the bit directing me to the column information of a certain location. So I'll be maybe pointing it right here. And then I write a bit data from that location. That's how we find the location of a certain data in the memories, right? In order to do that, we had to use a MIR, MDRs to store, read memory addresses from here and there. Yeah? 맞죠? And then we did take a look at some of the website memory cache, right? Faster memory, CPUs, right? What was an expensive CPU used to have typically have a large cache memory that's quite fast memory spaces that you can use, right? So basically we discussed a structure of the memory, how those things are organized, and just general property of the memory itself, right? So that was most of the stuff that we discussed. And properties of the memory as well, volatile. If the electricity is on, then you have your data ready. If the electricity is out, then some USB, flash disk, those things store information without a problem, but RAMs will disappear, the data will disappear. But today's application programs are so nice, then you don't feel like you're losing a data even if you turn off your computers. Like what? Which cases? 어떤 일이 있을까? For example, if you're writing something on your Microsoft Office, typing, somehow your computer power off. What happens usually? What's happening? Yes. Older versions of Windows, Microsoft Office, usually things disappear, but newer version of the Windows, they usually stays in, right? They made a temporary save files. Your stuff is mostly saved. But it doesn't sound like it, right? It says memory. I'm writing to a memory, right? When I open up the Microsoft Office, I'm typing in. As soon as I do that, I'm writing something to the memory space, right? What is the one way to save that data if there is no electricity, if there's no power? USB. Maybe if you do a constant backup to USB, that might be possible. Typically, you constantly, if you write something to the memory, your system is constantly trying to write that data into hard disk. If you write something on the hard disk, if power is off, those stuff gone or it's safe, right? So it's frequent, because of those frequent backup systems of today's nice programs, that we don't seem to be losing a lot of data even if there's no power, but that's actually what's happening. So they try to minimize any data loss. But in theory, anything in the memory, if there's no power, everything will be gone. Or other examples like those laptops or Macs. What happens if you close down your laptop cover? 어떻게 되지? Yeah, and what happens if you open it up again? If you have your original screens back, right? How is that possible? 어떻게 할까? In case of Mac, it's really fast, right? Back and forth. Sometimes they get the entire image of the memory space, the entire image, and then they store it, and then when you open it back, they get the image back to the memory, and so it looks like a really, really fast rebooting itself. 그 image file 뜬다 그러죠. If you try to burn a CD, they want a image files, right? So it's more of you getting an image of your system as soon as you close. As soon as you open it, you bring back the image into that memory space. So it's really fast looking system. Like, 그냥 이미지를 딱 닫을 때 이미지를 통째로 하고 있는 이미지를 통째로 디스크에 써놨다가 탁 열면 다시 이미지를 통째로 가져오는 거예요. 혹시 anybody using a ghost? ghost 같은 거? Ghost is usually typically used for backup purposes, or if you want to reinstall your Windows. Instead of you inserting a CD and click and install, some people prefer those type image recoveries. So you get the image of hard disk, and then you simply bring it back that image, so you have brand new Windows system ready. Right? So there are different type of techniques out there. Seems like you don't lose any of the data if there's no power and stuff. 약간 다른 얘기일 수도 있겠다. It may be slightly different examples, but still are related in some cases. Okay. How does your disk look like? How does your disk look like? Hard disk look like what? Hard disk look like what? Input as hard disk is typical input and output device, comes in two basic types. Those that represent information in human readable format for human consumptions. Those that store information machine readable form accessing by computer systems. Disk store information in what? Hard disk store information in what? 0101, 그죠? So it's not human readable, it's a machine readable. What's a disk? Hard disk. 디스크가 뭐야? Disk is a disk, right? Disk. So usually we're usually referring to magnetic disk. So they can store 0 and 01s you write into it, right? How does a disk look like? How does a disk look like? We know it's like a round format. 그죠? 이렇게 생겼지? And there is some disk arm moving around, spinning. 그죠? Spinning. Why does it spinning? Why do we need to make it spinning? 디스크에 들어갈 때. Have you guys seen old type of music players with the big record, black? It's the exact same. So if you want to move around within the record, if you want to listen to the track too, you move this stuff to the next level, right? So it's actually look like this. Almost similar design for the hard disk too, but it says fixed number of sectors in place, a concentric circle on the surface of the disk called track. Fixed number of sectors. There's a small block of 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0. Like that. There's a small sectors. Typical size of sectors, I think 4K. 아니다. 4K is much larger than 4K. A couple of hundred kilobytes. 아니다. Not a couple of hundred kilobytes. It's all different from old disk to new disk. 4K. And then this small sectors, if it's single track, consists of these sectors. So you have written down 0, 0, 0, 0 around this track. So if I wanted to read something from track 1, sector 2, this thing would be going right here. Moving on, reading from it, spinning in this direction. I try to go to that location, read 0101 from it. What happens if I read something from a hard disk? What's the next step? 어떻게 하지? You probably bring that to a memory. You write that back to the memory so users can use it. 그죠? This is why you don't shake your laptops. What happens if you shake your laptops too much? What happened to the hard disk? 그죠? There is this very tiny little gap between the surface and this moving arm. If they meet, then it will make a scratch. and your data cannot be recovered. 가끔가다 디스크에 스크래치 난다 그러잖아요. 요 움직이는 그 선이랑 얘랑 실제로 닿으면 안 돼. 실제로 닿지 않고 막 요만큼 떨어져 있어요. 닿으면 여기에 막 이렇게 상처 내는 거예요. What happens if you have a disrupted disk? Your disk is not good because you made a scratch on the surface. Can you recover some of the data? Sometimes if you pay them a lot of money, there is a companies to recover data. Maybe you might be able to recover data sets from here to here. Maybe not on this scratch. Sometimes you get a partial data recovered, right? That's why. Or sometimes even this disk broke, then you cannot recover. 그렇죠? 가끔씩 경찰들이 디스크 가져가서 뭐 복원했냐니 어쩌니 그런 얘기 하잖아요. 디스크 복원 못하게 하려면 어떻게 하면 될까? What can you do? Physically break everything, maybe. But there are some stories that you can destroy everything in your hard disk. I'm not so sure it would work. I even heard that some people try to put the hard disk into the water. I'm not so sure whether that works or not. But there are devices that you can delete everything's electrical charges, electrical devices. I'm not into those areas, but those are expensive machines out there. You can delete everything too, right? So anyway, we wanted to just take a look at the very basic structure of a disk itself. Tracks, sectors. Each single track consists of multiple sectors. This is a transferring unit to the memory. So moving arm, spinning disk, like that. But nowadays, some people don't use this magnetic disk, right? What are the other things that you can use? Yeah, SSDs, right? SSDs. Anybody using SSDs? And so some people do, right? If you have a lot of money, then you will be using SSDs, right? Or Mac Air. Mac Air do SSDs now? Some MacBooks probably use SSDs, right? Huh? Flash. Yeah, I don't know. I don't know too much, but yeah, I think it's somewhere around there. So this is a typical disk look like: spinning track, moving arm. This one, if I wanted to read this track, but this spinning only goes to one direction like that. Then if I wanted to go inside and move it back out again, it would take some time, right? Just like listening to the record, old-fashioned record. You have to bring it back, your headers, to the front. And then it would take some time to go back inside. 그렇죠? It only spins into one direction. 한쪽 방향으로만 도니까 안에 들어갔다가 밖에 있는 걸 다시 읽고 싶으면 다시 이렇게 또 나올 때까지 기다려야 되잖아요. 그렇죠? 마찬가지로. So there will be some difficulties, or not difficulties, there will be some delays when you try to read a data from certain locations. What if I wanted to read the data from here? Next data is right here. What can I do? I have to go back inside and move it back out again. It would be nice that I can move right away, but it's not possible. So that's why disk is slower than other devices like SSDs. You have to wait. You have to go to that position to read or write, and you have to move to the next position, but depends on where your next positions are, there will be some delays. There will be some delays. 여러분들 그거 본 적이 없어서 잘 모르겠지? 혹시 옛날 레코드판 집에 있는 사람 있어요? 본 적은 있어요? 그렇게 보면 이렇게 실제로 움직여야 되잖아요. 그 CD는 1번, CD도 마찬가지긴 한데 1번, 2번, 3번 트랙 이렇게 있듯이 걔는 실제로 이렇게 갔다가 다시 바깥으로 내야 되고 해야 되는 거죠. 실제로 움직여줘야 되니까. So there are categories to consider when you're dealing with this type of hard disk. Something called seek time. Seek time. Time needed to position the read and write head over the correct track. I need to go to track 2 somewhere here. So it's a time to go to track 2. That's a seek time, looking for. track 2. Latency, time for beginning of the desired sector to rotate under read and write head. So when I get there, how long does it take to read that data, particular sector, to get there? Because it's spinning, I have to go to the sector that I wanted to. When you try to buy a hard disk, I know we went to annuity last time. We only look at the what's it? Memory and CPU, right? So if you try to take a look at the hard disk, what is another another important metrics to look at if you try to buy a hard disk? What is a property of a hard disk they usually describe? Characteristics. Well, some hard disk says don't they? 아니야? They usually say that, right? 맞나? 56인가? You guys never seen that? Anybody try to buy a hard disk and hard disk have different properties? Some hard disk says 7200 RPMs. What does RPM stand for? Huh? Rotation per minute. Rotation per minute. So per minute it can rotate this many times. 7,200 times it can rotate. This disk usually a bit cheaper, and the disk size is probably a bit smaller. So its spinning speed is a bit less than this one, right? It means that the seeking time will be, if your disk spinning really fast, your seeking time can be faster. If it's spinning slow, your seeking time can be slow. So even with the same disk, if your disk achieves this many speed, then it's a bit expensive, less expensive. There are even more higher RPMs. 얼마더라? 13,000, 13,000? 13,000 RPM? I'm not so sure about the actual number, but something like that. Special type of disk, Scotch disk. The things that disks that you're using in what type? 요즘에 무슨 디스크가 많지? 뭐야 요즘에? SATA 2? 3? SATA 3냐 요즘은? Mini SATA, right? There is also, so if you take a look at the history of those SATA 1, SATA 2, SATA 3, this also changed as well. So some of the disk. There is special, other than SATA, something called Scotch. It's a very expensive disk. Rotation per minute is very high. Still expensive, but disk size still small. 이런 건 뭐 몇백 기가도 안 되는 디스크인데 훨씬 비싸요. 몇 테라 되는 디스크보다. Faster interaction to the users. If I click something, hard disk fast enough, then there will be less time for me to wait. Program seems to be a bit faster. Latency. So seek time, latency, transfer time. I go to track 2, that's the seek time. In this track 2, I like to go to a certain sector within track 2, that's latency. After you got to that sector that you wanted to, read it and send it to the memory. Send it to the memory. The time for entire sector to pass under the read and write head, have its contents read into a written or from the memory. So if I want to write it or read it from a disk to the memory, and that's the total time that I write my data or read my data from a disk. That's called transfer time. Transfer time. Data, whenever I type, it's on the memory. What's in the memory will be written to the disk. Sometimes not all my data within the memory, so I have to ask the hard disk to read some of my data, bring it to the memory, I read that memory, and then I do something within my program. That's the typical step, 3 steps. So there will be a lot of transfer between these steps, transfer times between these steps. The general architecture of all this type of devices. Don't forget, we're still in this architecture. Disk is somewhere around here. So I have to read it from a disk, and I have to give it to the memory. Okay. We were just discussing how long it takes to read a disk or write to a disk using seek time, transfer time, and latency. We just simply described that. Transfer time from here to here. Okay. Seek time and latency happens within the disk. Okay. Of course, there are like I/O buffers, control logics. Even within the disk, there's a small memory space to write a data, but those things are there to fast things up. It's not too much concern for our scope of this course. I/O buffer, control logics, I/O controllers. I/O controllers? What might be the other terms to describe it? I/O controllers. Well, maybe you guys hear the terms like firmware. Sometimes your smartphone asks you to update your firmwares. Firmware update, right? Firmwares or drivers, if you want to think it like drivers. 그래픽 카드 사면 드라이버 깔으세요 막 이렇게 나오죠. 하기야 요즘에 드라이버 깔 일이 없지만. That's why they say data interrupt. Don't worry about it. When you actually try to exchange the data, you need help from a processor, CPU. Those controlling mechanism is something called interrupt, but that's later. So now we know how the basic structure of a disk devices. Sequential access storage devices does not require all unit of data identified by unique addresses. Direct access storage devices much faster in accessing individual piece of information. Blah blah blah. Sequential access just from 1, 0 to whatever. So it simply means that because I'm gonna go from the beginning anyway, so I don't need to. Everyone doesn't need to have the address itself. You might thinking as maybe disk, and this one is SSDs, for example, SSDs. What might be the problem with the SSDs? SSD의 문제는 뭘까? What might be the potential problem of SSDs? SSDs usually bit more expensive, right? Disk size still small, but it's expensive. Is it faster? Yes. Why is it faster? Comparing to the disk, why is it faster? 왜 빠르지? Well, first thing I will look at, there is no seek time. It's not spinning stuff. SSD right to a memory chips, right? So I can go right there. If I want to go to that certain location, I can go directly. I can point out. Just like the memory structure that we looked at, similar ideas. On the other hand, hard disk, if I wanted to go to that location, I have to go through other tracks to get there. So even from the beginning, there is a difference. So, but SSDs requires much more complicated techniques because you try to write something in the middle. So there's an issue to how to organize the data bits within the system. 그리고 there is usually a limitation of how many times that you can you can write to SSDs. There is a life cycle of SSDs. SSD는 한 몰라 정확한 숫자는 모르겠는데 몇십만 번, 몇만 번 이상 이렇게 디스크에 쓰면 갑자기 수명이 확 줄어요. 넣는 속도가 갑자기 확 줄어요. 디스크는 그런 게 없는데. 그래서 SSD는 수명이 좀 있어요. 요즘에 수명이 많이 길긴 했지만 그러니까 하드디스크는 차례 찾아가니까 그 타임이 좀 늦긴 한데 그런 이슈는 없는데 SSD는 그냥 메모리처럼 쭉 있는 거니까 내가 가고 싶은데 탁 한 번에 갈 수 있는 대신에 거기에 있는 걸 고치면 앞뒤로 붙어 있는 거를 어떻게 고쳐야 되고 막 이런 이슈가 좀 있어요. 그리고 자꾸 쓰다 보면 몇 번 이상 쓰게 되면 수명이 확 줄어갖고 속력이 확 줄어요. 그럼 반밖에 안 돼. 원래 샀던 거에. 그래서 한 SSD 한 2, 3년씩 쓰면 갑자기 시스템이 조금 옛날하고 별반 다르지 않을 것 같은 느낌이 들 수도 있어요. Different type of input and output devices. I just simply bring up the example between SSDs and hard disk. Two complete different approaches. What we care is the transfer time. How fast can we get the data from these disks? And how can we organize nicely using this type of controllers? SSD 얼마나 하나? How much is the SSD nowadays? 몰라. I didn't check. 얼마? 몇 기가 얼마야? 40기가? 그밖에 안 돼? 아닐 텐데. We usually go to 64, 128, and 256. Why? Why those SSDs goes like that? The hard disk goes like 10, 20, 30, 50, 100 gig. But SSDs goes like 64, 32, 64, 128, 256. Why in different numbers? 그죠? Chips. 여기 왜야? Because of this. 그죠? It grows, it's memories. It goes by 2 to the ends. 그죠? 디스크는 아니잖아. 그죠? 바이너리 칩의 메모리 사이즈니까 n이 늘어나니까 16진수 이렇게 늘어나는 거죠. 2의 몇 승으로 하면 2의 몇 승이면 32예요. 뭐야? 2의 5승인가? 2의 6승 하면 얼마야? 6승. 그렇게 올라가는 거죠. 2의 7승. 0101 칩으로 올라가니까. 서킷으로 올라가니까. 오케이. gibberish. I've discussed that. So, ALU, arithmetic logic units, subsystems that performs addition, subtraction, and comparison for equality. Addition, subtraction, comparison for booleans sounds like a very basic circuit. It's a combination of circuits, right? Add circuit, subtraction circuit. So, comparison, probably using a NOT gate and gate. So, maybe. Components, registers. The things that consist of the ALU is registers. Like I say, register is small memory space, very fast memory space. Interconnection between components and ALU circuitry. Registers, small storage cell that holds operands of an arithmetic operation that holds its result. Simply put, is it add? One register is storing, is it addition, subtraction, those type of information. Some other register will store a output of those operations. 1 plus 1 is what? 그것도 대답을 안 해? 1 plus 1 is what? 2. Yeah, so you store a 2 in somewhere in the register, some register. Bus, like I say, the line on the top, the connecting memory, 뭐였지? Memory, ALU, and I/O devices, right? So it's an electric path. 이거 뭐 뻔하지 뭐. So this is one of the examples for 3 register ALU organization. So I don't know what this ALU will be doing. Maybe let's say it's doing addition. It's been asked to do addition. So what's in the register A, what's in the register B, add it together. They write it down to register C. Each small storage cells, small memory locations that you can use. 이거 why are we speaking like that? Because we wanted to introduce you to machine languages later. Control units store program sequence of machine language instructions stored as binary values in the memory. Control units have fetch, decode, execute. Let's take a look at the examples. Might be simpler. Like these. So in the actual machine level, they give instructions like this. Whatever I wanted to do, let's say, opcode add register 1, register 2. It means then add register 1, register 2. That's my instruction. I'm telling the machines to do that. And each add have its own binary code. Let's say add is 0, 0, 0. And register is 1 is 0, 1. Register 2 is 1, 0. Then 0, 0, 0, 1, 0, 0, 1, 1, 0. I just did a binary encoding of this instructions. We'll see what it means. Machine language instructions. Instructions that can be decoded, executed by the control unit of the computer, which means we tell CPU what to do in binary formats. Binary for 0, 1, 0, 1 only. Operation code field, unique unsigned integer code assigned to each machine operation recognized by the hardware. Unique means what? Unique가 뭐야? 뭐야? 번역도 못해? Unique is what? 다른 거랑 구별이 확실하게 되는 거죠. 그죠? There is no duplicates. Unique, unsigned integer. Unsigned integer is what? Unsigned가 뭐지? 양수음수 안 가리고 there's no plus or minus. Unsigned integer code assigned to each machine language. So each example of operation: add, subtract, store, fetch, those type of the instructions. So each instruction will have special integer code later. So we tell those integer code to the CPU, then CPU know what to do. Instead of we tell the CPU add, we tell them add is 1, 1, so 1, 1. CPU know that they will do an addition soon. Address field, memory addresses of the values in which operation will work. Examples that we saw, we tell which register is where. And in 2 registers, we're going to add values in those 2 registers. Simply tell where your values are, your datas are. And it will look like that. Example, let me just go to the example first. Like this. Add 102. Later, add can be translated into some other code too. Load 101. Get the value of location 101. Let's load 101. That's my instructions. So this is actually your program look like. But we don't program in this way, right? We usually program in C and high-level languages. Those things will be translated back into like this. 우리 CS 프로그램 짜잖아, 그죠? CS 프로그램 짜면 they eventually will be translated like this. So CPU can understand. CPU will not understand if and else. They will not understand your pseudocode, right? So we need to translate into a machine language. That's what's going on. So if I take a look at from the top, address 100 has a has a value of A. Address 101, somewhere in the memory or register address, value of B. Address 102, value of C. So I work with those stuff. Maybe if this one, I wanted to do this. Value of C, B, and C, get the value of B and C, add it, and write that into location of A. So A equal B plus C. This is what I wanted to do. So first thing that I wanted to do is get the value of B. Load 101 to a register. One of the registers that I can use for this program, a small memory location. And what? A small location, when I called load 101, the value of B, where B was, B would be right here. And next line says what? Add 102. Load 101, add 102. I'm gonna add to this location. So register will have the value of B plus C. Okay. So it's very stupid step-by-step instructions. You do. Store 100. Store means store. Right? Save. But 100 is what? Location of B. Location of A, right? Load 100. Store. Store this value to location 100. So somewhere in A will have value of B plus C. You just program this using a register, small machine language instructions. So this is my program. This is my program of adding two numbers, B and C, and storing in C. Machine language. Later, this load, add, store will have their own number. For example, load might have a 1, 0. Add might be, just call any number, 1, 1. Store 0, 1. So if I decode that, that probably 1, 0, 1, 0, 1, 1, 1, 1, 0, 2, 0, 1. This is my program in binary. And each time I tell CPU this, I tell CPU this. So just convert the machine language into a binary format. So we just convert everything into 0, 1, 0, 1 ways. So, and CPU depends on which CPU. Each CPU have their own instruction sets. Certain good CPU can maybe even able to do a multiplication. So a CPU have an instruction set called multiply. 이건 CPU에 따라 다 틀려요. CPU will have different set of instructions. But these are the basic instructions. Add, store, load. This is what CPU can do. So. 지금 우리 뭐 하는 거야? 혹시나 또 뻔한 얘기하는데 못 알아들을까 봐. CPU가 알아들 수 있는 말로 번역해 준 거죠. 그죠? add, load, store 이건 CPU가 알아. 어떻게 하는지. CPU의 설계에 따라 얘네들은 기본적으로 CPU는 뭔 뜻인지는 알아. 그래서 CPU한테 CPU 언어로, 머신, 기계 언어로 얘기해 주는 거예요. load는 10으로 딱 정해져 있으니까 10, 101 하면 load 101. One by one. Line 1, line 2, line 3. Okay. That's what's happening. That's what's happening. What about the second example right here? This one is not addition. This one is even a bit more complicated. This is a piece of code that you can do. It says if A is bigger than B, then set C to value A, or else set C to value B. So it's actually asks you to do a comparison. Compare is CPU already understand what it means to do a compare. Compare location 100, location 101. If so, jump to 54. 54 right here, line 54 for example. And do this, otherwise move 101 to 102, maybe this. Set C to A. This one looked like you're programming C, pseudocode. It looked like pseudocode. You just simply translate into a machine language. So one of your assignment questions will ask you to do that. Ask you to convert your pseudocode or language program into that machine level languages. Just make it more dumber program. Make it more dumb program. 완전 기본으로 생각하면 되죠. 내가 사용할 수 있는 메모리도 딱 정해져 있고 거기다 어떻게든 꼈다 넣었다 넣었다 뺐다 하면서 내가 원하는 걸 하면 되는 거죠. 그렇죠? 어차피 2학년 때 아마 컴퓨터 아키텍처, 컴퓨터 구조에서 아마 비슷한 숙제가 나오긴 할 건데 여기서 조금은 할 거예요. 이 인스트럭션 셋이 다 CPU마다 다 같을까? CPU마다 조금씩 다 틀려요. 조금씩 다 틀려요. Hopefully you get the basic idea of what we try to do. That's why I wanted to go to that example first, and then the next slide. So, instruction set is set up all operations that can be executed by a processor. CPU understands. CPU has a set of instructions to execute. They know what it is. So we already seen many different instructions, at least 5. 뭐였냐? Load, add, store, compare, jump. 또 뭐였지? Move as well, right? There must be many. And there are 2 different type of architecture, CPU architecture, CPU design. When you design the CPU, it sounds very scary, right? Design a CPU. Intel CPU, AMD CPU, they have all different architecture. It also means that they have a slight different set of instruction sets within the CPU. Two big types. One is called reduced instruction set computers, RISC chips, RISC CPUs. The other one is complex instruction set, CISC CPUs. So RISC design, CISC design is a common term they use. Reduced instruction set computers, reduce means you already seen it. Load, add. This is very simple type of instructions, right? If your CPU can support these type of instructions, they follow then RISC type design. RISC type design. RISC 형태로 디자인된 CPU들은 이렇게 짧은 거 add 기본적인 거. Includes as little as 30 to 50 instructions. So there are really dumb CPUs out there. It's not even CPU. It's small processors, 4-bit processors, 2-bit processors. 무슨 뜻이야? Things that you can buy out there, like controlling RC car 같은 거. If you want to drive RC models, they have a small CPUs. Only have maybe few instructions that they can do. 4bit면 what is the maximum number of instructions they can have in theory? 4bit짜리 CPU면 2의 4승이겠지? But they only use a 2-bit for instructions, the other bits for doing other stuff. 2-bit, 4-bit, 16-bit CPU. Ring a bell? 옛날에는 그렇게 부르죠. 8비트 컴퓨터, 16비트 컴퓨터, 32비트 컴퓨터, 64비트 컴퓨터, and then they don't stop calling it. So they call it different names. That's what they mean. Instruction sets, how many they can handle. Also, how complex those instructions can be. RISC design machines, CISC, doing very complex operations. Maybe single operation here should be done with multiple RISC designs. So 2 different types. I just looked it up. Is Pentium which architecture? Pentium CPUs. Intel Pentium CPUs. 뭘까? I also looked that up too. Pentium is basically CISC design, but they will use some of the RISC instruction within it. So it's a bit of hybrid, the 2. So modern CPUs, I guess they use a CISC design chips, or smaller processors. It's much suitable for RISC design architecture. So machine language instructions continues. Classes of machine language instructions: data transfer, arithmetic, compare, branch. We already take a look at it. Data transfer. What was the instructions was doing a data transfer? Load, store, load and store. Arithmetic, add, 그죠? Compare. There was one instruction set called compare right away, 그죠? Compare. Branch. Branch was what? Jump to the point. 그죠? The example was saying, jump to 54, branch. 이렇게 나가는 거. 딴 데로. I skip this part, go to 14 right away. So there are 4 different type of instruction set, typical instruction sets that you can work with. Right? Basic component classes. Control unit registers and circuits. You need registers to hold the memory space. The temporary, you can think of it as a temporary memory space to do this type of stuff. But registers are limited. Registers are limited. Sometimes you only have a 2 register to work with. So you have to figure out the way of doing it. Program counter holds the address of next instruction to be executed. It's okay. Instruction register hold a copy of instruction fetched from a memory. It's okay. It might confuse you more. Instruction decoders determine what instructions in the IR. It will come up in next few slides. Anyway, examples of simple machine language instruction sequences from top to bottom. Again, I will ask you one of these either in your finals or midterms or your assignment. So you need your practice. I mean, it's not a pseudocode anymore, right? Pseudocode, we didn't care about the memory spaces, and if you need A, you can just use it. In this case, you need to be careful. You need to take a look at where is it in the memory space. You also have to consider how many registers do I get to use it. Right? Things like that. It's a limited environment from this point on. So, wow, programs will be very long. So, 이거 even with this lines 1, 2, 3 lines translate into 1, 2, 3, 4, 5, 6, maybe more. So, machine language instructions will be longer than typical program. 가끔가다, for example, sometimes the virus companies, antivirus companies like what is popular antivirus companies, vaccine companies, 뭐 있어? 써보진 않아서 들어는 봤어요. What else? 카스퍼스키 뭐 이런 거 있지 않나? 맞나? 이름이? 카스퍼스키가 맞나? Russians, Korea have unlab, 그죠? Unlab. Sometimes they actually take a look at, once they catch a virus, they wanted to take a look at the virus structures, how those things are programmed. They actually take a look at this. They don't have the source code, 그죠? They don't have the source. Sometimes they don't have the source code. So they recover this type of machine instructions from those data they can have, and they try to guess. Oh, this one tell me jump to a certain location. Oh, this might be doing something wrong in that location. 이렇게 끊겨서 나온 정보를 가지고 유출을 많이 하기도 하고 일반적으로 그렇게 하기도 한다고 알고 있습니다. opcode address field. So opcode is given to decoder. Decoder will give the actual sequence of numbers that representing that arithmetic operation or that instruction operations. 이거 뭐 필요 없겠다. So here's an example. The opcode 000 instruction add. 001 load, 010 jump, 111 finish. If I give that opcode part, opcode must be agreed upon. I say opcode 3 bits, then everything has to be 3 bits. 3 bits, give it a decoder, and decoder was selecting lines too, right? Selecting lines too. So it will select the add operation, enabled add operation. It's simply telling the CPU. Decoder is in the between to give a signal to these lines. 여기서 000 주면 이 라인이 불 들어오게, 001 주면 이 라인이 불 들어오게. That's the job of the decoders doing it. 물론 옵코드가 3비트라는 건 미리 정해져 있어야 되겠죠. 코드 3 bits. Any questions for today? 질문?